Alright, here we go. So, this is the last section of this chapter on identity, solving equations, inverse trig functions. We have three different double angle formulas. So sine of twice an angle, sine of 2 theta is equal to 2 sine of theta, cosine of theta. So what these do is they take sine of 2 times an angle and write it as sine and cosines of an angle without having that doubling in it, that constant out in front of the angle. Cosine of 2 theta equals cosine squared theta minus sine squared theta, and then I want to add the other two here. We had 1 minus 2 sine squared of theta, and then the one we proved, which was 2 cosine squared theta minus 1. So add those to the mix. We use those to substitute and rewrite things all the time in calculus. And then tangent 2 theta equals 2 tangent theta over 1 minus tangent squared theta. So those are the three double angle formulas. Way back before calculators, they would use, that was the same story in the other lesson, but they would use this to find exact values of something like maybe sine of 15 degrees, where you could double 15 degrees, you get 30 degrees, and so you could do sine of 15 degrees, or you could do this is a double angle formula. So you could use the double angle formula to find angle measurements in between the ones that we know from the unit circle. But of course, we could plug those into our calculator right now. So all you really need is familiarity with these, just to be able to substitute them out so you can simplify certain expressions, equations, things like that for calculus. Yeah.
What would you use these for?
Yeah, just for finding, like, remember the sum and difference ones? We could use them to find, say, exact value of cosine of pi over 12.
Well, like, what would you do with that? Like, I'm not.
Oh, okay.
Like,
No, I know.
for like
Just to evaluate equations. So if you're solving equations, you would do that. We have calculators, so we just get the decimal approximation. So that's the quick answer to that. But the other way we use this is in calculus. Before you do the derivative or integral of certain functions, we will apply these identities to basically to simplify those expressions before we can integrate or differentiate. So that's where you'll see it next year. The ones I remember using the most in terms of Calc 1 were the power reducing ones. We use the power reducing ones combined with a method called partial fractions. Like there's a method for integrating certain functions, and so that combined with partial fractions to do kind of opens up a whole family of functions that you can then integrate. So that's what we do. That's primarily what we use these for, is just to rewrite. So we're not memorizing, we're not going to worry about memorizing any of these. This one right here, cosine squared of x, is a very useful one. You will use this one next year. Same as sine squared of x. It takes something that's squared and makes it so that it's to the power of 1. And then you can break this into pieces and then integrate it. What's neat about integration and differentiation is that you could like integrate or differentiate 1/2, which is the easy problem. And you can integrate or differentiate cosine of 2x over 2, which is fairly easy. It involves a little bit of what's called the chain rule along with the integral of cosine. So it allows you to be able to integrate and differentiate functions, but you have to rewrite them first. That's a lot of what we do. That's why you learn algebra, is it's a lot of simplifying, rewriting, so that you can do something else with it. Right? And then ultimately, it's all about mathematical modeling. So we can model things in real life with trigonometric functions, and then that opens up all these things, tools that we have to analyze those functions. It's like that tidal sine wave project. There's a lot more to that than what we did, like getting a trigonometric function to model that, and then what you can find out is that you could differentiate that thing. That's one of the calculus things, to find out what maybe a certain rate of change is. So we had time versus speed. So you could get a rate of change of the changing of the tides at a certain place along the coast by using the derivative. And so, or you could find, I don't know, I'd have to think more about this, but the integral actually, Newton and Leibniz discovered the integral gives you area under a curve. So you could find the area, accumulated area underneath that curve of that sine wave as you go along. And then they started taking those and revolving them around an axis and finding out that you can make a two-dimensional mathematical model, revolve it around the x or y axis, and then create three-dimensional mathematical models for real-life phenomena. So those are pretty neat things. Calculus is really a pretty useful tool, much of which we can do with algebra. But calculus is just so much more efficient and effective than some of what we do with algebra with that. So, anyways. Oh, more than I wanted to know. So these problems right here go back to, they kind of connect to the last problem I did on the previous notes, where you're given the ratio for sine, cosine, or tangent of an angle, and so we draw a picture. We're drawing a right triangle. The dead giveaway here is, when I look up there, I see sine of theta equals -4/5. Now, if I saw sine of theta equals -1/2, I could actually figure out theta, because that's one of the ratios of one of the special angles, right? Like pi over 6, or pi over 3, depending on if it's cosine or sine. But when you see something that's not a 1/2, a root 3 over 2, a root 2 over 2, or a 1 or a 0, they're probably asking you to draw the triangle and go ahead and use the Pythagorean theorem to find the missing side length and then find the other trig function. So here's what we're going to do. Draw a picture here. Do you know what this is telling me? Where am I to draw my right triangle according to this? Between pi and 3 pi over 2. Which quadrant is that in?
Left, second.
Left, bottom one. Yeah, so it's down here. So it'll look like this. There's my generic triangle. There's my right angle. There's my theta. This tells me the opposite side is 4 and the hypotenuse is 5, and I like this one. I don't even have to do any squaring. Yes, it's a Pythagorean triple. This right here is 3. I like it when the triples show up. So there's our picture. And so we could find cosine of theta. What's cosine of theta? Cosine, and is it positive or negative? Negative, because it is in the to the left of the y-axis, so -3/5. Now, I'll tell you, we're going to need to know tangent of theta as well as we go through and calculate these, because I think I asked you to calculate sine of 2 theta, cosine of 2 theta, and tangent 2 theta. So we're going to use, boom, 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 these 3 formulas, okay? So, what's tangent of theta going to be then, according to my picture? Yeah. And is it positive or negative? Yep. Remember, all students take calculus. Those are the positive ones. All of them are positive here, just sine here, just tangent here, just cosine. Or you could think of it as negative over negative is positive. Okay? All right, here we go. So, sine of 2 theta, according to the formula right here, is equal to 2 sine of theta cosine of theta. So I'm just going to copy that down. And sine of theta is -4/5, so I'm going to plug in -4/5 for sine of theta. And cosine of theta is -3/5, so I'm going to plug that in and then evaluate it, and that's it. So we have 12 25ths, 24 25ths. So 24 25ths. So you just plug in the values of sine and cosine of that angle that we drew in the third quadrant. So my picture is a picture of theta. If I wanted to find sine of twice that angle, I could do it. Look at it in a minute. All right, let's do cosine of theta. Or cosine of 2 theta, sorry. So cosine of 2 theta. So cosine of 2 theta, it's your choice. You can use any 3 of these. I think I'll just use the top one. So we have cosine squared minus sine squared. So cosine squared theta minus sine squared theta. And cosine theta is equal to negative 3/5. So this ends up being negative 3/5 squared minus sine of theta is equal to negative 4/5. So I plug in negative 4/5 for sine of theta. And so that's 9/25 minus 16/25. And 9/25 minus 16/25 is negative 7/25. All right, and then the last one is tangent of 2 theta. So let's do that here. Tangent 2 theta. Yeah, 3. So it is 2 tangent of theta. So we have 2 tangent theta. I'll just write down the formula first. Over 1 minus tangent squared. So I'm going to substitute in for tangent theta that 4/3. And then on the bottom as well, 4/3 squared. So tangent theta is being replaced with 4/3. Every time you see a tangent theta, it's 4/3. Remember, tangent squared is the same as tangent of theta quantity squared. So tangent theta gets replaced with 4/3. Unfortunately, with the tangent double angle formulas, we have a complex fraction. It's kind of a bummer. So the goal with the complex fraction is to get one fraction on the top. That's easy. It's 8/3. And then another one on the bottom. It's a little more work here. So we have 1 minus 16/9. So that's 8/3 over 9/9 minus 16/9 is negative 7/9, and then that equals 8/3 times negative 9/7. And so we can simplify here. 1, that's 3, and multiply straight across, negative 24/7. Yeah. So I was just applying each of those 3 formulas. How does number 2 differ from number 1? Do you know what the difference is here? The decimal, yes.
You're in a different quadrant.
In a different quadrant and a different function. So, well, if I have a decimal, how am I going to figure out what the hypotenuse is? You could write it as 0.4/1 if you wanted to, but I don't really want 0.4 to be my adjacent side. So 0.4 is also known as 2/5. So that's probably what I would do, is think of this as cosine theta equals 2/5. And then you would draw your right triangle in the first quadrant. That's what this is saying. So in the first quadrant, you have a right angle here, theta here. The adjacent side is 2. The hypotenuse is 5. This one is not a Pythagorean triple. Yeah, we'd have 2 squared plus a squared equals 5 squared. So a equals 25 minus 4 is 21. So we have root 21. So then we'd have our sine theta equals opposite root 21 over 5. And then tangent theta equals opposite root 21 over 2. And then you would go through the same process again, plugging in those values. I don't think we'll go through that whole thing again. I'm going to let you try some.
I was going to say, that's a really well drawn triangle. Like,
How it turned out? Okay. I just draw the same triangle in each one. I'm not trying to give it together.
it's very clean, my triangle.
Its scale is a bit off. It should be taller. Alright, so there it is. Do you understand what we would then do to find if I asked you for sine of 2 theta, cosine 2 theta, tangent 2 theta? It's plugging into a formula. We kind of haven't known what to do sometimes on these ones where you have to draw the right triangle. Hopefully it's, where you're seeing it. When it says sine of theta equals, and then there's a ratio of 2 numbers, that gives you 2 out of 3 pieces of the triangle. And once you have that third piece of the triangle using Pythagorean theorem, you could get any of the other 5 trig functions. You could find cosecant of theta if you wanted. What would cosecant of theta be in problem 1? If sine of theta equals negative 4/5, what would cosecant of theta equal? Yes, negative 5/4. You can switch it around. Okay? And then these formulas, that's why we're calling them formulas. They call them identities or formulas, but we're just plugging in. Evaluate. All right. These next 2 on here are called, this is called the power reducing formula. This is one of the more heavily used ones in as you're learning your integration techniques in Calc 1. So sine squared of x equals 1 minus cosine of x over 2. And then this is the other one. Cosine squared of x equals 1 plus cosine of 2x over 2. It's called power reducing because it's reducing the squared sine and cosine function down to a first degree cosine and sine function. Now this can be applied to even higher powers. Watch this. If I could actually make this to the 4th power here, and it would change this in here a bit, but you could apply this to higher and higher powers, and that's where we use it in calculus. All right. So we're going to use the power reducing formula to simplify cosine squared of x over 2 minus sine squared of x over 2. See how this works. So this is I'm going to use both of them. So cosine squared of x over 2 is this one in blue here. And so this is taking place of x in the formula. I probably should draw the arrows elsewhere, but I don't want to draw them there. That'll confuse you. It's this one that I would use here. So this right here is going to go in here and right here. See how they match? So I'm asking for sine squared of x over 2, so I'm going to replace x in the formula with x over 2. Do you see the advantage of that? So let's go ahead and do it. We're doing the cosine squared one first. So it's 1 plus cosine of 2 x over 2 over 2, and so this term becomes this. Then we have minus sine squared of x over 2 becomes 1 minus cosine of 2 times x over 2 all over 2. So this one is that, according to the formula. So all I'm doing is plugging in the angle right here for x. So this is 1 plus cosine of x all over 2 minus, okay, think of it this way. If you put a bracket around that and I distribute, what are the, maybe think about the signs here. It might even be helpful if we go to the next step here and write this as 1/2 plus cosine of x over 2 and then distribute the minus sign, right? I mean, what I really have here is minus 1 minus cosine x over 2. And when I distribute, I'm going to get a minus 1/2 and a plus cosine x over 2. So what does this simplify to?
2.
Yeah, the 1/2s are gone. This equals 2 cosine x over 2, which is just cosine of x. If you really wanted to complicate things, you could rewrite cosine of x as cosine squared of x over 2 minus sine squared of x over 2.
Why would we want to do that?
Yeah, you wouldn't. Yes. Okay. Next question. Don't stress. It's just a formula. You're just rewriting things. That's what we do in algebra and in trigonometry. We rewrite things. There's a purpose for rewriting them. I can't show it to you yet because it will come in. It's going to come in calculus. It wouldn't make any sense if I showed it.
So it's just like spoiler alert.
Spoiler alert, yes. You'll use this technique to rewrite things before you integrate them. What I can tell you. As a matter of fact, in the calculus book, there's whole lists of integrals based on this technique. You could. Typically what happens is you only use a select number of or types of functions within a certain job or function or whatever. Yeah, and most of it can be done on whatever mathematical software it is on your...
Well, I was using my CAD program last night. I was making a design and it just... It does all that.
I know, but somebody had to write that. All right. Here's... This is really starting to show you a little more of why we might need to know these, is we're going to actually use these identities to rewrite and solve. So here's an example. Sine of 2 theta equals cosine of theta. We're trying... So we have this function, sine of 2 theta. We have another function, cosine of 2 theta. Let me just show you on the calculator what I'm asking you to do here. This might help you a little bit. So we see on here that there are 1, 2, 3, 4 solutions to this equation between 0 and 2 pi. We're going to find them now using some algebra and trigonometry. So here we go. I have sine of 2 theta equals cosine theta. First of all, I have 2 different variables. Also, this argument is different than this one. So we want to at least get the arguments to be the same. So we're going to replace sine of 2 theta with the double angle formula. What is that? So it's just a substitution. So just maybe make a note here. Substitute. Okay? And we're going to replace it with 2 sine of theta, cosine of theta, equals cosine theta. So I'm just doing a trig substitution. Now I have an equation I can solve. You've actually solved this very equation before.
No.
Yes.
When?
It's been on a quiz or a test from when we were doing equation solving. That wasn't that long ago. Last semester. I put it on in this form. We didn't know how to go from here to here, but now we do. How do you solve this equation? Maybe you'll recognize it once I show you the process for it. Actually, I think all these fall into the same category.
We'll use that.
A little more specific than that. They're all solving by factoring. You've done this before. I'll show you. No. Has to do with factoring. That's why you spent your entire algebra math career since 8th grade factoring. Okay? Yes.
Where do you see the subscript come in?
Right here. I'm looking at that equation. I can't solve it as is. But when I substitute sine of 2 theta, or substitute 2 sine of theta cosine of theta for sine of 2 theta, now I can solve it. So that is primarily what we use identities for, is for substitutions, so we can solve equations or integrate differentiation factors. Okay? Right? We okay on the substitution here?
Yeah.
So now, this is called factoring out the GCF. What's the GCF of these two terms? Yes. And what's left over when I factor out a GCF of cosine of theta? Then the next step is called the zero product property. Learned it in Algebra 1. I know. So cosine theta, I know, but you saw it again in geometry and then again in advanced algebra 2. This is why you are all here. You're good at this. Now we have to get used to seeing factoring in terms of other functions. That's the tricky part, right? I'm not asking you to factor the linear function x. I'm asking you to factor sines and cosines. It's a little hard. So now here's where the stuff we talked about at the very end of the semester comes in. This is just theta equals arc whose cosine is 0. Yeah. So what are the values between 0 and 2 pi in radians where the ratio is 0, or where the x-coordinate, if you will, is 0? That's all we really care about, is the x-coordinate. It's cosine. Pi over 2 and 3 pi over 2. Okay. So we have two of the solutions. Pi over 2, 3 pi over 2. How many solutions did we expect from our picture? 4. There's 2 of them. So right here we have sine of theta equals 1/2. Are we okay with that so far? Add the 1 over, divide by 2. So theta equals inverse sine, or arc whose sine is 1/2. So what does theta equal? 0 to 2 pi. This is, I'm not asking for the one function output. It's 0 to 2 pi, pi over 6, and second quadrant just a little bit up, just before 6 pi over 6, 5 pi over 6. So pi over 6 and 5 pi over 6. And so those are all the solutions between 0 and 2 pi. There are 4 of them. Not a bad idea to plug them in. We already saw that there were 4 on the graphing calculator, so I'm going to call it good. Okay. Remember the extraneous solutions possibility? I think that showed up on our quiz end of the semester. All right. Number 5. Number 5. So we have sine of something and cosine of something mixed in. Any ideas on what to do on number 5 before we go to solve it? Yeah, well, we can't distribute sine, but we can apply the sine formula.
Oh, you like sine? I saw that.
Yeah, the sine alpha, cosine beta thing.
Beta.
It's this formula right here.
Yeah, that is.
Now I'm pulling on. So this is equal to sine theta cosine pi over 2. So with sine, remember they're different, but the sign remains the same, plus cosine theta sine pi over 2 plus cosine theta equals 1. What is sine of theta cosine of pi over 2 equal to? What is it? What happens with this term is what I'm asking. What's cosine of pi over 2? Ah, okay, 0. What's sine of pi over 2? Good. So this term right here with the sine in it is now gone. Now I have an equation just in terms of cosine. I can solve this. Right? We've got cosine theta times 1 is cosine theta. Cosine theta plus cosine theta is 2 cosine thetas. I know. It is. I mean, cosine theta is just like your x, right? They're like terms. Okay, so cosine theta equals 1/2. So you can ask for, okay, what is the angle theta such that this is true? Where is the x coordinate on the unit circle equal to 1/2? That's what this is asking in words. You might even want to write that. What's that? Pi over 3. And where else? 2 pi over 3, it's negative 1/2. So pi over 3 and where else? Okay, pi over 3 and 5 pi. Now, let's write these down. We could maybe go and plug those back in to check and make sure they both work. Well, you gotta be a little careful, or you could graph the left side and the right side and look and see if they intersect. But the graphing calculator won't show if there are things like certain issues. You have to zoom in on it so much to see them. It won't show holes very well. The color does better. I just want to warn you that when we get these solutions, it's worthwhile to plug them in, check them when you're doing it. Both of those work. We're going to have some extraneous solutions pop out here in the next 2. Yeah.
So when you get your answers, like there's no restricted areas. All the unit circle count.
It does. Well, all the units circle from 0 to 2 pi based on this. It's whatever it says here.
Oh.
There are no restricted areas yet.
So if it said pi, then it would only be.
Yes. What's that?
There's no.
The restricted areas aren't the same as they are for the functional outputs. So, for example, cosine, inverse cosine, has a range of 0 to pi. I just told you to find all solutions from 0 to 2 pi, so we're ignoring the normal functional output. That's what I'm saying.
So you're just like, let's add more complicated stuff. Why not?
All right. This guy is balancing on the high wire. Careful. These are the ones that have the extraneous solutions in it. You got to be a little careful here. So we have 4 sine squared of x over 2 plus cosine squared of x equals 2. Somehow we need to get this all in terms of one variable. Which formula do you think we might use to accomplish that?
Power removing?
Yes, the power reducing one, right here. It says the second one takes a sine squared and changes it into cosine. So this can be replaced with 1 minus cosine 2x over 2. But x isn't really x. What is x in this problem? So it's 1 minus cosine of 2x over 2. It will end up being an x. All over. I'm going to move my guy out of the way here. Plus. That would actually be, if I could just go over here.
Move people.
I would never be like Jordan. Sling him to the corner or whatever. All right. So look at how much this will simplify quite a bit. These cancel. You can distribute the 2. And you can also rewrite this as just cosine of x. Okay. Can we solve that problem? Now, this is something we've already solved before, so I guess I'm answering my question. Can we solve it? Yes, we can solve that. This is like having a...
I don't know what you're thinking of me.
This is like having an x squared and an x in the same problem. It's just more factoring. Oh, no. So we can get rid of the 2's, right? Subtract 2 from each side. We could rewrite this as cosine squared of x minus 2 cosine of x equals 0. Now it's set equal to 0. This is like having x squared minus 2x equals 0. It's the same thing. X squared minus 2x equals 0. Write it down if you need to. You can solve this, okay? There are 2 solutions, possible solutions, let's say. So we have greatest common factor is cosine of x. What's left over is cosine of x minus 2 equals 0. We set each factor equal to 0, so cosine of x equals 0, or cosine of x minus 2 equals 0. So x equals arc whose cosine is 0, or x equals arc whose cosine is 2. You'd add the 2 over, take inverse cosine of each side. Right, x equals inverse cosine of 0. Where is that true? Arc whose cosine. In other words, where is the x coordinate 0? Yeah, pi over 2. Pi over 2 and 3 pi over 2. Where is the x coordinate on the unit circle equal to 2? Where is the x coordinate on the unit circle equal to 2? That's what this is asking right here. Never. Nowhere. Right? So this one you just have to say not possible, right? And so your 2 solutions are just pi over 2 and 3 pi over 2. That's it.
What are you talking about? Everything is possible.
This isn't. You can't have an x if you draw a circle of radius 1 centered at the origin. You cannot have an x coordinate with 2 that is on the circle. You can't do that. All right, the last one, number 7. What do you think would be a useful substitution here?
The science
The other one we didn't use.
The one we didn't use, yeah. I think that's a good choice. So 1 minus 2 sine squared x equals 2 minus 2 sine squared, oh, it's not x, it's theta. So theta. And now we have an equation all in terms of sine. All right, so let's see if we can go ahead and solve this. Maybe set it equal to 0, huh? Move everything over. What happens when I add 2 sine squared theta each side? 1 equals 2, huh? What does that mean? Yeah, there's no solution. So, if I were to do what I did in the beginning of this lesson on solving trig equations, I graph cosine 2 theta. I graph 2 minus 2 sine squared theta on 0 to 2 pi. What would you find? There would be no intersection, okay? No intersection. That's what that means. There's no place, there's no value of theta which the two are equal. No solution. That's what that means. I've been thinking about this a little bit because I'm about to introduce my Algebra 1 students to systems of linear equations. I mean, that's the very beginning of what we're talking about right here. Intersections of functions, right? What do they have in common?
You want to introduce those to us?
I introduce.
Yes.
Switch out like beginning to it type stuff.